This tutorial introduces Scikit-learn, guiding you through building and evaluating machine learning models with ease. The first step in any machine learning project is to set up your environment by importing the essential Python libraries. For this tutorial, we will use NumPy for numerical computations, Pandas for data manipulation and analysis, Matplotlib for creating visualizations, and Seaborn for making statistical plots more attractive and informative. These libraries form the foundation for preparing, exploring, and visualizing your data before applying machine learning algorithms. The next step in our machine learning workflow is to import all the necessary modules from Scikit-learn, which will allow us to load data, pre-process it, build models, and evaluate their performance. First, we will use the load diabetes function from Scikit-learn datasets to access the Diabetes Dataset, a commonly used dataset for regression tasks. To prepare our data for modeling, we will import train test split from Scikit-learn model selection, which allows us to divide the dataset into training and testing sets to evaluate how well our model generalizes to new data. Since features in real-world datasets often have different scales, we will also use standard scalar from Scikit-learn pre-processing to standardize our features, ensuring that each one contributes equally to the model. For model building, we will use linear regression from Scikit-learn linear model, a simple but powerful algorithm for predicting continuous values. Finally, to evaluate our model's performance, we will import mean squared error and R2 score from Scikit-learn metrics, which provide insights into the accuracy and explanatory power of our regression model. Together, these modules form a comprehensive toolkit for performing end-to-end machine learning with Scikit-learn. Next, click on the Run button to execute your code. This will load all the imported libraries and modules, prepare your environment, and allow any initial setup commands to take effect. Running the code at this stage ensures that all dependencies are properly loaded and that there are no errors before you proceed to the next steps, such as loading the dataset, pre-processing the data, or training your machine learning model. This step is crucial for making sure your workflow runs smoothly from start to finish. The next step is to load the Diabetes Dataset into our workspace. We will use the load diabetes function from Scikit-learn to do this. Once loaded, we can separate the data into features and targets. The features, which contain the input variables, will be stored in X, while the target values, which we aim to predict, will be stored in Y encode. This looks like assigning diabetes equals load diabetes, then X equals diabetes data for the input variables, and Y equals diabetes target for the target values. This separation is important because machine learning models require clear input, features, and output, targets, to learn patterns and make predictions effectively. We will convert the Diabetes dataset into a Pandas data frame for easier exploration and manipulation. We can create a data frame by passing the data X as the values and the feature names Diabetes feature names as the column names. We will also add the target values Y as a new column named target. Once the data frame is created, we can use the head function to display the first few rows and get a quick look at the dataset. This step is helpful for understanding the structure of the data before proceeding with pre-processing and modeling. After converting the Diabetes dataset into a Pandas data frame, you can now see all the features as columns. Viewing the data frame in this way helps you understand the dataset at a glance, see how the features are organized, and identify which variables will be used as inputs for the model versus the output we want to predict. Next, we split the dataset into training and testing sets using the train test split function from Scikit-learn. We set test size equals 0.2 to reserve 20% of the data for testing, while the remaining 80% will be used to train the model. Additionally, we use random state equals 42 to make sure the split is reproducible, so every time we run the code, we get the same training and testing sets. This ensures consistency when training the model and evaluating its performance. The training set will be used to teach the model patterns in the data, and the testing set will allow us to check how well the model generalizes to new, unseen data. The next step is to scale the features so that all input variables have a similar range. Scaling is important for many machine learning algorithms, including linear regression, because it ensures that features with larger numerical values do not dominate the model. We use standard scalar from Scikit-learn pre-processing to standardize the features, which transforms them to have a mean of 0 and a standard deviation of 1. The next step is to scale the training features so that all the input variables are standardized. We do this by using the fit transform method of the standard scalar object. This method first calculates the mean and standard deviation of each feature in the training set, fit, and then applies the transformation to scale the data. Transform. We assign the result to xtrain scaled so that the scaled training data is ready for model training. Next, we scale the test data using the same scalar fitted on the training set by calling transform. This ensures the test features are on the same scale as the training data. After preparing and scaling our data, the next step is to train the linear regression model. We start by creating an instance of the linear regression class from Scikit-learn, which represents a linear regression model. Then, we fit the model to our scaled training data, xtrain scaled, along with the corresponding target values, ytrain. During this fitting process, the model learns the relationship between each feature and the target by calculating the best fitting line that minimizes the difference between the predicted and actual target values. Essentially, the model finds the coefficients, weights, for each feature and the intercept so that it can make accurate predictions on new data. Training the model on the scaled features ensures that no single feature dominates due to its magnitude, which helps the model learn more effectively. After training the linear regression model, the next step is to make predictions on the test data. We use the predict method of the trained model and pass the scaled test features, xtest scaled, as input. The model then outputs predicted target values, which we store in ypred. Comparing these predicted values with the actual target values, ytest, will allow us to evaluate how well the model has learned from the training data and how accurately it can predict unseen data. After making predictions with our linear regression model, the next step is to evaluate its performance. We compare the predicted values, ypred, with the actual target values, ytest, from the test set. Two common metrics for regression evaluation are the mean squared error, MSE, and the R to the power of 2 score. The MSE measures the average squared difference between predicted and actual values, giving an idea of the model's overall prediction error. The R to the power of 2 score indicates how well the model explains the variation in the data, with a value closer to 1 meaning a better fit. We can use Scikit-learn's mean squared error and R2 score functions to calculate these metrics, and then print the results to see how well our model performs. Finally, we can visualize how well our linear regression model performed by creating a scatter plot of the actual versus predicted target values. On the x-axis, we plot the actual target values from the test set, ytest, and on the y-axis, we plot the predicted values, ypred. We can label the x-axis as actual target, the y-axis as predicted target, and give the plot a title such as actual versus predicted target. This visual representation helps us quickly see how close the predicted values are to the actual values. Ideally, the points should lie along a straight diagonal line, indicating perfect predictions. After evaluating the model, we see that it has a mean squared error, MSE, of 2,900 and an R to the power of 2 score of 0.45. The MSE measures the average squared difference between the predicted and actual target values, so a value of 2,900 indicates the magnitude of the prediction errors. The R to the power of 2 score of 0.45 means that the model explains about 45% of the variance in the target variable. The next step to improve the model's performance is to explore several strategies. First, we can tune the model's hyperparameters, such as the number of trees in a random forest, the maximum depth of trees, or learning rates and other algorithms, to optimize its predictive power. Second, adding more relevant features or engineering new features from existing data can provide the model with additional information to learn from. Third, we can try different machine learning algorithms, such as gradient boosting, XGBoost, or support vector regression, to see if they perform better. Finally, increasing the size of the dataset, handling outliers, and addressing missing values can also improve the model's accuracy. Combining these strategies systematically can help achieve a more robust and higher performing predictive model. Another regression method is the random forest regressor, which is an ensemble learning technique that builds multiple decision trees and averages their predictions to improve accuracy and reduce overfitting. To use it, we import random forest regressor from Scikit-learn ensemble. We create a random forest model with 100 trees, and estimators equals 100, and set random state equals 42 for reproducibility. Then, we fit the model to the scaled training data, xtrain scaled and ytrain. After training, we make predictions on the test set, xtest scaled, and store them in ypredrf. Finally, we can evaluate a model performance using the R to the power of 2 score, comparing the predicted values with the actual target values, y-test. You have completed this tutorial on machine learning with Scikit-learn, including data preparation, scaling, training linear regression and random forest models, making predictions, evaluating performance, and exploring ways to improve your models. Keep experimenting with different datasets, features, and algorithms to strengthen your skills.